right. Good afternoon, good morning, good evening, depending on where you are. Today we have the great pleasure to welcome Roee Ozeri from Weizmann Institute in Israel. He's a professor at the Weizmann Institute. He also did his PhD over there and then came to the US, to NIST in Boulder, to study quantum information processing with laser-cooled ions, and subsequently returned to the Weizmann Institute. He has received many prizes and awards. It's an impressive list of research breakthroughs he could report. I really think he is the dynamic decoupling grandmaster, and therefore lots of people profit from his work. His research is really focused on two aspects. There is one experiment where they do quantum computing metrology with ions, chains of ions, and then he's also investigating atom-ion interactions, having overlapped ensembles of cold atoms and ions. And I think that's what he's going to talk about today. So, Roee, please go ahead.
Thank you very much, Christian, and Shimon and Lindsay, and thank you very much for having me on Vamos. This seminar has been keeping me alive during COVID and has been a special treat since as well. So let me see. So do you see the presentation right?
Looks good.
Oh, good. So what I'd like to tell you about today, or rather tonight here in Israel, is about a field of research that has developed in the last 15 years or so, in which groups have been investigating atom-ion interactions in the ultracold regime. Let's have a laser pointer. So what you see here in this image, the little red dot here, is the fluorescence image of a strontium plus ion, and the background, the cloud around it, is a cloud of about 100,000 optically trapped rubidium atoms at microkelvin temperatures. So just as a very short background, both trapped ions and neutral atoms, laser cooled, have been investigated since the end of the 70s, the beginning of the 1980s. They're rather different platforms. So trapped ions, interact through their very strong Coulomb interaction. That's why they form these Wigner crystals, very often one-dimensional. The very strong Coulomb interaction prevents their wave functions from overlapping when they're very cold, and that's why, for example, their spin statistics doesn't matter at all. But on the other hand, they're pristine quantum systems. They're very well isolated from their environment, and that's why they're used for quantum computing ends. They're used as optical atomic clocks for the sake of precision measurements and more and more. Neutral atoms are a little bit different in the sense that when you laser cool them and trap them, they interact, but they interact in a way that their wave functions clearly overlap. And in that sense, whether you're speaking about bosons or fermions, you get a very different behavior and a very different system. And people have been studying the behavior of collective ensembles of neutral atoms and their interactions. Dipolar gases would be one example. Superfluid Mott insulator investigations in optical lattices would be another. And neutral atoms as well are pristine quantum systems and have been used for the quantum computing and optical clock end. In the past 15 years or so, research groups have started looking at mixtures of ultracold ions and ultracold atoms. And what would be the motivation to do that? Well, I think that one motivation, if we're honest about it, one motivation is that we can, and it's a new playground. And very often in the history of science, once we can create a new playground, usually that new playground gives new results that we've never thought of. Another motivation is to study ultra-cold atom ion chemistry. In fact, chemistry in outer space happens through interactions of atoms and ions. This is the longest range attractive interaction that you can find in outer space. And that interaction actually dominates interstellar molecular formation. In addition, you could think of these ions as highly localized, again, pristine quantum probes that you can use in order to study ultra-cold gases. And in this case, you could harness all the toolbox that was developed for the purpose of quantum information studies with trapped ions for the study of ultra-cold gases. And these systems are also interesting because they could emulate different condensed matter systems. So for example, the ion is going to be dressed through the interaction with the atomic dipoles to form charged polarons. You could think of interactions that are mediated between trapped ions, similar to the RK-KY interaction, condensed matter. You could think of condo crystals. So there's a lot of motivation that was used when studying these systems that came from the world of condensed matter. And since 2009, we could see close to 20 experiments worldwide that studies these systems. And I've listed here a list which I'm sure is not exhaustive, and I apologize if I left experiments out. But you can see that this is a very pluralistic community, and you can find experiments using all sorts of pairs of atoms and ions. The experiments that I listed here in black are experiments in which the atoms are in a magneto-optical trap. What does that mean? That means that they're not in their electronic ground state. They're constantly scattering photons. It also means that temperatures, or the atomic temperature in these experiments, is limited to the millikelvin or hundreds of microkelvin range. The red experiments are experiments in which the atoms are trapped in optical or magnetic potentials, and evaporative cooling can cool them to very, 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 very low temperatures. So how do these ions and atoms interact? Well, at the long range, they interact through their polarization potential. In short, the electric field that the ion produces polarizes these atoms, produces a dipole moment, and that dipole moment interacts with the field. Because the dipole moment is proportional to the field, the interaction is proportional to the field squared, leading to an attractive 1/r⁴ interaction. This interaction was studied classically initially by Paul Langevin about 100 and some years ago. And what Langevin has shown is that with this interaction, if a collision occurs above some critical parameter, then all that happens is that the atom and ion deflect ever so slightly in a glancing type collision. However, if the impact parameter is below the critical impact parameter, what happens is that the two spiral inwards until a short range collision occurs, and then the two can depart. So these Langevin collisions are collisions that happen below this critical impact parameter, happen at a rate which happens to be independent of energy. That is because the cross-section for a Langevin collision is proportional to 1/√² of energy, or 1/the velocity, and therefore the rate, which is proportional to the density times the cross-section times velocity, is energy independent. And this energy independent rate is really the rate that governs the inelastic processes or chemistry rates between atoms and ions. It also controls the rate at which momentum transfer, significant momentum transfer, happens between ions and atoms. Now, how do we connect this classical picture to the quantum world, where the connection to the quantum world can be written in the following way? We can think of the Langevin cross-section as a sum over the cross-section of colliding through the different partial waves between the atom and the ion. So the Langevin cross-section is going to be given by 4 pi over k squared, and then a sum over the different partial waves from the 0 S wave partial wave all the way to the maximal partial wave that the collision energy can allow for. There's a 2L plus 1 factor, and then a sine square of the phase which the wave function acquires when scattering over this partial wave. Now, when I have many, many partial waves, I can think of this sine square factor as averaging to 1/2. And when I do that and sum from L equals 0 to L max, I actually recover the classical Langevin cross-section expression. Now, clearly, long range is not the only element in the collision. When you go to short range, when you go to molecular distances, then the interaction between atom and ion is being replaced by a repulsive potential. This is due to the exchange interaction. One unique feature of the -1/r⁴ potential is that it's relatively long range. And because it's relatively long range, when we look at the position of the centrifugal barrier, for example, of the P wave, the first centrifugal barrier that you can think of, you can see that it's relatively far away from the center of origin. In the case of rubidium atoms and strontium plus ions, which is the mixture we use in our lab, this comes out to be about 1/4 of a micron. And what does it mean? It means that in order for the de Broglie wavelength of the atom-ion wave function in the center of center of mass coordinate system to be larger than this length scale, one needs extremely low temperatures. In our case, it's slightly below 100 nanokelvin. That means that if we want to go into the quantum collision regime, if we want to go into the S-wave regime, we actually need the atom and the ion to be well below a microkelvin and tens of nanokelvin, in the tens of nanokelvin range. I should say that -1/r⁴ potential is the last stop where you can still use S-wave, the S-wave limit. When you look at -1/r⁴ potential similar to dipolar interactions, the S-wave limit doesn't exist at all. So here the S-wave limit exists, but you need to be extremely cold in order to reach the S-wave limit. How would you tell that your collisions are occurring in the quantum regime, or in the S-wave or close to the S-wave regime? Well, a first indication of that would be signatures of quantum interference in the scattering amplitude. And one canonical example of that is that of scattering resonances. So here an example of one of the scattering resonances people would look for when going to low temperatures. And this collision resonance happens when the collision energy is on resonance with a quasi-bound state that is held by the centrifugal potential. These resonances are called shape resonances, and they're predicted for atom-ion mixtures. But I should say that because we know that classically the Langevin cross-section is energy independent, really any significant energy dependence of the scattering and the reaction rate would already be a departure from the classical behavior and a possible indication of quantum scattering effects. And resonances are just one radical example of energy dependence of the scattering cross-section. Now, when we look at real systems like strontium plus and rubidium, it's not just a single molecular potential, but rather a zoo of molecular potentials. Each one of these molecular potentials at a large separation would correspond to rubidium plus and strontium, or rubidium and strontium plus at different electronic states. Actually, one thing to notice in most of these mixtures between alkaline-like ions and alkali atoms is that the collision entrance channel is not necessarily the ground state of this system. So, for example, when we think of the strontium plus ion in its ground state colliding with a rubidium atom in its ground state, this molecular potential is not the ground state of this system. And the reason for that is that if I look at rubidium plus, which is a noble ion, and strontium, which has a pair of electrons in the ground state, the energy of this configuration is significantly below the energy of these two atoms in their alkaline form. So when I enter the collision, if the collision is elastic, I exit on this molecular potential as well. However, an inelastic process can occur in which charge moves between rubidium and strontium plus, leading to a strontium and rubidium plus configuration, and in this case, emitting an IR photon. And what you can see here in this movie, which has some probability of playing, for some reason the movie is not playing. But in any case, what the movie does show is the crystal of 8 little bright strontium plus ions slowly churning into rubidium atoms. In our system, such charge exchange collision happens at every about 10 to the 4 Langevin collision, and it happens radiatively when the rubidium atom and the strontium ion collide on the singlet molecular potential, emit a photon, and find themselves on the singlet potential of strontium, neutral strontium, with a rubidium ion that is a complete scalar. So this kind of completes the background that I wanted to give on ultra-cold atom-ion systems in general. I'll shortly describe the system that we're using, and again, in this community, you can see different machines that serves different purposes. In our case, we have a machine that uses 2 vacuum chambers. In the upper vacuum chamber, we collect rubidium atoms in a mott. We load them into an optical trap. We can evaporatively cool them or not, and then load them into a one-dimensional optical lattice. And then by scanning the frequency difference between the lattice beams, we shuttle the atomic cloud about 30 centimeters down into the center of a lower vacuum chamber in which an RF pole trap is positioned. And then these atoms are overlapped with a single or a few trapped ions. In this case, we can transfer these atoms into another optical trap and then overlap the ion with a cloud, with a cold cloud of neutral atoms. Or if you want to study the effect of a single collision, and we also want to control the energy of that collision, we can actually scan the atomic cloud using the 1D optical lattice across the ion, and we can control the density such that in a single pass, the probability for a single Langevin collision is significantly below 1, and then study the effect of this collision. How do we know how many collisions we have? So here is an example of how we can calibrate the number of collisions. We can actually control the energy of the ion by applying an electric field that displaces the ion from the center of the pole trap and into regions where there is a very strong oscillating RF field. In this case, the kinetic energy of the collision would be determined by the amplitude of the RF fields that push the ion back and forth. Now, how do we know that the ion collided? If the ion did not collide, then all this kinetic energy does is it imposes micromotion sidebands on the lasers that interact with the ion. And then if we want to shelve the ion on a narrow optical clock transition, in our case, it's a transition between the S1/2 and the D5/2 electronic levels, we can do that easily. However, if the ion collides with an atom, all this kinetic energy is being transferred to temperature. Doppler shifts in this case are at much lower frequencies, and they completely smear out this spectrum of atom-ion interactions. In other words, they take the ion outside of the Lambdiki regime, and then shelving fails with very high probability. So by monitoring the shelving failure as a function of ion energy, we can actually directly measure the probability for a Langevin collision. Keep in mind that the Langevin probability is independent of energy in these high energies. So we can tell for sure that the probability for collisions between the atoms and the ion is well below 1, and we know what it is. Right. So I guess that this is a pretty good place to stop and ask everyone on the seminar if they have questions.
Yes, indeed. There is a bunch of questions. Most of them related to the special features of this combined ion neutral atom system. So let me start. First question is, so the RF fields you need for your Paul trap, do they also affect the neutral atoms by any means?
So that's a good question. They negligibly affect the neutral atoms. Of course, these are electric fields, so they polarize the atomic wave function and interacts with the atoms through the dipole moment, which is formed. But that interaction is significantly orders of magnitude smaller than the interaction of the atoms with the optical fields that are much larger and at a much higher frequency that is closer to the atomic resonances.
Then next question. So you described these interactions between the atoms and ions, and one question is, how much variation is there if you have different species of atoms, different species of ions, or is this all, let's say, within the same order of magnitude?
So the long-range interaction, the polarization potential, does not depend on the ion at all, because all these ions have produce the same electric field. They interact through their charge. There is a difference when you look at the atomic polarizability. So the atomic polarizability would vary from one atomic species to another, but the variation is not great. Having said that, there's a very big difference between the different pairs of atoms and ions that are used in terms of the dynamics, which we observe later on, and that has to do, and this would be apparent in the next few transparent slides, and that is mainly due to the mass ratio differences between the different pairs that you use. But in terms of the long-range interaction, the polarization potential is very similar for all these atom-ion pairs.
And somewhat related, so the trap depth, right, for the ion and for the atoms is hugely different. Has that a lot of impact on what you can do in your experiments? How does it affect your experiment?
That's absolutely right. And the way it affects our experiments is that most collisions do not affect the fact that the ion is trapped. The ion is trapped in a trap that has a depth of 10,000 Kelvin or so. So the likelihood of a collision with an atom at microkelvin temperatures is not very likely to impact the trapping of the ion. It could heat the ion up, as I'll show shortly, but it's not kicking the ion out of the trap. Atoms, on the other hand, are routinely kicked by collisions with the ion. That's something else I wanted to mention, is that because collisions, for the most part, kick the atoms out, and because very often we study single collisions, we don't know with which of the atoms the ion collided, we end up studying this dynamics by investigating the ion. And we can do that with very good fidelities. The disadvantage is that every time we repeat the experiment, we get 1 bit of information. So this experiment has the experimental treat that it has the repetition rate of a cold atom experiment. We can repeat, we can shuttle a new cloud of neutral atoms into the ion trap maybe 3 times a second. But every time we do so, we get 1 bit of information. So to get good statistics, you really have to integrate over a long time. So this is an experiment for patient people.
One last question maybe for this part. So could quantum information applications or atomic clocks profit from, you know, being set up in such an engineered neutral atom plus ion system? Like, for instance, you could get access to cold alkali ions, like with noble gas configuration. Is there anything advantageous or going in this direction?
So I think eventually you could look at these hybrid, so people investigate hybrid systems actually for both ends. In the case of quantum computing, people often look at the advantages that you could get by taking two different quantum computing platforms and using them together in order to benefit from their respective advantages. And people have been, people have been showing tremendous success with both these systems. So either, for example, Rydberg atoms in Twizzler arrays and crystals of trapped ions. I'm sure that by putting these two quantum computing platforms together, one would be able to benefit. Similarly, in optical clocks, trapped ions have a relatively low systematic error budget, whereas neutral atoms, give much better projection noise and are much more stable. So combining both such systems, you could perhaps enjoy the greater stability of the neutral atom ensemble while investigating the trapped ions. So you could think of directions in which these two systems would give you technological benefits. I don't think these experiments are at that stage yet. So we're really still taking the baby steps in these hybrid systems.
All right. Yeah, let's continue. There'll be another opportunity for questions later in the talk.
Absolutely. So as I mentioned, the sort of the holy grail of this domain of research for a while was to try and push into the low temperature regime and see quantum effects. And as I mentioned, low temperatures here are much lower than you need, for example, with neutral atoms to get to the S-wave regime. So instead of seeing S-wave behavior at the millikelvin range or hundreds of microkelvin range, in our case, you need to go to the few microkelvin down to the tens of nanokelvin range, really depending on the reduced mass of the atom-ion pair that you're working with. About 10 or 11 years ago, in a seminal paper by Marco Satina, who at that time was a graduate student working in the voltage group at MIT, Marco has shown that when ions are trapped in pole traps and interact with neutral atoms, with ultracold neutral atoms, even if both species start out extremely cold, there is a limit to the energy with which the atom and ion collide. And this limit is due to the fact that when the atom and ion approach each other, the polarization potential pulls the ion away from the RF null of the pole trap. And when the ion moves away from the RF null, the RF fields of the pole trap actually perform work on the ion and inject energy into the collision. And when Marco calculated the size of this energy scale, he could show that this energy depends on the trap parameters, so the charge, the RF frequency, and so on. But it also depends on the reduced mass, or the ratio between the atomic mass and the ion mass. And this energy for very light atoms and much heavier ions can be rather small, but for atoms and ions that have similar mass, this energy can be rather large, and in fact can hinder the ability of these systems from going into the quantum regime. And indeed, the first experiment we did in these systems, and that was sort of 8 or 9 years ago, we cooled the ion to the ground state of the pole trap in all 3 dimensions, and then overlapped it with a cloud of microkelvin temperature atoms. And instead of seeing the ion remain in the ground state, we actually saw the ion heat up as a function of the number of Langevin collisions it underwent with the neutral atoms. What you see here is the temperature of the ion as a function of Langevin collisions. And you can see that after about 10 Langevin collisions, the ion was already at a millikelvin temperature, which indicates about 100 microkelvin in terms of energy that the atom heats up the ion when it's in the trap, even though the atom starts in the few microkelvin range. This is indeed due to the presence of oscillating RF fields in the trap during the collision. Something else that we've discovered is that after the ion heats up, it actually develops not a thermal distribution, but rather a power law distribution. In our case, it's a power law distribution with a power of about 2, which means that this is really a funky energy distribution that doesn't even have an average. So it's a pretty radical energy distribution that suggests that the dynamics here is far from thermal equilibrium. This is a highly non-equilibrium statistical mechanics. And clearly, with this type of system, we can't take the system into the S-wave regime. So if you'd like to go into the S-wave regime with these systems, well, it says Microsoft PowerPoint is not responding. I apologize. I'm going to stop sharing. And then I'll try to reshare. Do you see my screen well now?
Yeah, it works again.
Works again. So in order to get to the S-wave regime, other research groups have actually turned their focus into mixtures of very light atoms, and the lightest you can conveniently work with is lithium, together with very heavy ions. In this case, the Geritsma group in Amsterdam used a mixture of ytterbium plus and lithium. In this case, the S-wave scattering is higher because the reduced mass is lower. It's roughly the 10 microkelvin range. And also the heating mechanism due to the RF fields is on par with that. And using this system, you can see here an indication of the spin exchange probability as a function of energy departing rather strongly from the energy independence that Langevin collisions predict in the classical case, and an indication of quantum behavior in the S-wave regime. Another example comes from Freiburg, from Tobias Schatz's group, in which they used a barium ion, again with lithium atoms. And in this case, again, going close to the S-wave scattering regime was possible. And in this case, the cross section for a 3-body recombination process was measured. So it's really ion loss from the trap, was measured as a function of the magnetic field, showing very nice Feshbach resonances. So from about 2 years ago or so, the atom ion community was able to go into the S-wave regime and show scattering resonances. So after this overview, what I'd like to do in the remaining time is to quickly tell you about 2 experiments that we did with our system. In the first experiment, what I want to tell you is that despite the fact that we're using a system in which going into the S-wave regime is impossible, we're stuck at the 100 microkelvin energy range. S-wave scattering for us occurs at 100 nanokelvin. We have temperatures that are 1,000 times larger than was necessary to go into the S-wave regime. We can still see signatures for quantum interference effects in scattering. In other words, we can see signatures for S-wave physics very far from the S-wave regime. The other experiment I'd like to tell you about, if time permits, is another way with which the presence of the pole trap affects atom-ion collisions. And this is the observation of trap-assisted formation of atom-ion molecules. You know that usually when you have two free particles that collide, the center of mass motion and the relative motion are decoupled from each other, and therefore in inelastic collisions, you can't form a molecule. However, in the presence of a trap, center of mass motion and relative motion can be coupled, and elastic collisions can lead to the formation of bound states. So let's start from the first topic, which is signatures for S-wave physics, far from the S-wave regime. So what is the tool with which we search for these quantum interference effects? The tool is that of an inelastic process of spin dynamics, spin exchange. So we studied the dynamics of the spin of a single strontium ion when we immerse it in a cloud of rubidium atoms. And there have been previous experiments along these lines by the Cole group back then in Cambridge, UK. So what you see here is the probability of the ion being in different spin states as a function of the number of Langevin collisions it undergoes with neutral atoms when we initialize rubidium atoms at different ground state spin states. So what do you see here? You see that if we initialize the ion, and this is a strontium-88 ion, it doesn't have a nuclear spin, so therefore no hyperfine manifold. It can either be in the electronic downspin state, m equals -1/2, or the electronic upspin state, m equal 1/2. If we initialize it in the spin down state, which is the red data here, and initialize rubidium in the 1-1 state in the hyperfine manifold, we see that the ion spin remains in the down state at the 90% level. However, if we start the ion in the spin up state, we see that after about 10 Langevin collisions, the ion spin aligns itself with the spin direction of atomic rubidium, again at the 90% level. So this effect that we see here is the effect of collisional spin pumping of the trapped ion by the polarized cloud of rubidium atoms around it. Why is this happening only at the 90% level? It happens at the 90% level because on top of spin exchange, we also have some coupling of angular momentum from the spin degrees of freedom to the angular momentum of the two nuclei of the atom and the ion through a spin relaxation process. But the spin relaxation process is about a factor of 5 slower than spin exchange, and that's why we can actually use collisions in order to align the spin of the ion together with that of the cloud of atoms around it. However, when we initialize rubidium in the 1-0 state, meaning that there's no preferred direction to the spin of rubidium atoms around the ion, we see that it doesn't matter if we start the ion in spin up or spin down state. After about 10 Langevin collisions, the ion spin direction is completely randomized. Actually, that led to a really nice observation. I've shown you before that we're not at the ground state of this collision channel, and the emission of a IR photon can take us from the ground state of strontium plus rubidium into the singlet ground state of strontium and a rubidium plus noble ion. However, that process can only proceed when we start in the singlet state of the collision. Now, if we align the spin of the ion with that of the spin of the atomic cloud, then the singlet fraction there is much smaller. The overlap with a triplet state is much larger, and we can show that we can actually affect the cross section for charge exchange by controlling the spin degrees of freedom of the atomic cloud, which is kind of nice. So how can we think quantum mechanically of the cross section for spin exchange? So what we follow here is a model that was developed by Alex Dalgarno in the 1960s. Similar to the Langevin cross-section in quantum terms, the way we think of spin exchange as a collision that occurs both on the singlet and the triplet manifolds of the collision of the molecular potentials. And then we can think of up-down, so the ions spin up and the atoms spin down, as an even superposition of singlet and triplet m equals 0, and down up as an odd superposition of singlet and triplet m0. Now, if a collision occurs and a phase is being acquired between the singlet and the triplet, then this can turn up-down into down-up and lead to spin exchange. So if you want to know what the cross-section for such spin exchange collision to occur, again, we sum over different partial waves. We have the 4 pi over k squared factor. We sum from L equals 0 to the maximal partial wave we can allow for. We have a 2L plus 1 factor, and then we sum over the sine squared of the phase. But unlike in Langevin collisions, we don't look at the total phase which is acquired. We look at the phase difference between colliding on the singlet and the triplet states. And because this is a spin exchange, we also need to look at the matrix element connecting our initial state to our final state when looking at the product of Pauli spin operators between these two spins squared. Now, in the semi-classical regime, when we have many partial waves, and remember, we work at temperatures that are 1,000 times above the S-wave scattering regime, this sine square function should average to about 1/2. And because we know the input state and the output state, we can calculate this matrix element squared and compare our measurements to what we expect to see from the semi-classical approximation. What you see here in the red lines are the semi-classical approximations, and the data that we've measured is about twice as large as what the Dalgarno semi-classical approximation would predict with a sine squared of about 1/2. In other words, it seems like our sine square averages to 1 and not to 1/2. And that is very peculiar. You do not expect that in the semi-classical regime. So together with our colleagues, Timur Tserbul and Masato Morita at the University of Nevada in Reno, we went on to calculate this cross-section using coupled channels calculation. And in this calculation, we changed the gap between the singlet and the triplet of this collisional channel. And indeed, we're able to observe that the cross-section shows perfect interference fringes. And that was very peculiar because, again, we don't expect to see quantum interference effects so far away from the quantum regime. And when we investigated this process a little closer, and what you see here is the results of a WKB model, we calculated the phase which is acquired on the singlet and the triplet given some calculated molecular potentials. We've noticed that while the phase on the singlet and on the triplet, which is displayed here by the blue and the red symbols, fluctuates violently across the sine squared 0 to 1 interval, meaning the different partial waves have completely random phases, the phase difference between the singlet and the triplet, which is shown here by the black data, is actually fully stable and locked between different partial waves. And it took us a little bit of time to understand why that is. And the reason for that is the very large separation in scales between the short-range physics that occurs on molecular potentials, due to which the phase between the singlet and the triplet is lifted, and the physics of centrifugal forces, which happens at distances of hundreds of nanometers, very far away. So in regions where different partial waves acquire different phases, these are regions where centrifugal forces act, there is no phase difference between singlet and triplet. But in regions in which the phase is being lifted between singlet and triplet, centrifugal forces do not play a role at all. So in other words, we can see S-wave-like behavior with many partial waves involved. And this is what we set out to measure. Now, we can't really play with the energy difference between the singlet and the triplet. We don't have that knob in the lab. But what we can do is actually measure across different strontium plus isotopes. Now, if we see a very strong deviation in the cross-section for spin exchange between different strontium plus isotopes, that would be a very strong suggestion of this mechanism in play and the observation of quantum interference effects far from the quantum regime. So to describe how we were able to measure the cross-section for spin exchange between different isotopes of strontium plus and rubidium atoms, we had to come up with a good techniques to do that because we don't have all the laser systems to work with the different isotopes of strontium plus. Nevertheless, we wanted to measure the effect of inelastic scattering on different ions of strontium plus. And in order to do that, we took inspiration from a very nice technique that was developed in the last 15 years or so, which is called quantum logic spectroscopy. In spectroscopy, very often one is interested in performing precision spectroscopy with species that do not lend themselves easily to techniques of laser cooling, to techniques of state measurement or state initialization. And in order to do that, pioneering experiments initially at NIST and then at PTB used quantum information techniques in which one ion served as a probe ion and one ion serves as a spectroscopy ion. And in short, the mechanical effects of light interacting with the spectroscopy ion were transferred through the strong Coulomb interaction to the logic ion, allowing for the reading out of the optical transition occurring on the spectroscopy ion. And using these pioneering techniques, probably some of the best optical atomic clocks today work on such techniques. Molecular spectroscopy has improved by orders of magnitude. Highly charged ions are spectroscopically investigated. This is really a very powerful technique in molecular and atomic spectroscopy. We use a very similar line of ideas, but not in order to study atom-photon interactions, but rather to study ion-atom interactions. So the technique, in short, is the following: instead of trapping just a single ion that will interact with a cloud of ultracold atoms, in this case, we trap a crystal of two ions. One of them is a logic ion, in our case, strontium-88 plus, and the other ion is the chemistry or the interaction ion. Now, when the cloud of ultracold atoms passes through this crystal, if the interaction with the chemistry ion or with the interaction ion is exothermal, for example, and releases energy, we can detect this energy release through the strong Coulomb interaction with our logic ion. So in order to detect spin exchange collisions, the way we go about that, we initialize the rubidium atoms in the F=2 manifold. The hyperfine energy gap between these two states is at, in terms of energy, is at 330 millikelvin. We initialize the ion in the spin down or spin up state. And then if due to spin exchange, hyperfine energy is released and the rubidium atom is transferred between the F=2 and the F=1 manifold, we can again detect the failure of shelving on a narrow optical clock transition and detect that indeed spin exchange has occurred. We use this technique in order to measure the spin exchange cross-section over 4 different isotopes of strontium plus, strontium-88, strontium-86, strontium-84, and strontium-87. And we found that while all the even isotopes of strontium have shown a very similar collision cross-section, strontium-87, the odd isotope, is actually shown a cross-section which is about half as much. Now, together with our colleagues at the University of Warsaw, Max Walewski, Matthew Fry, and Michal Tomza, who performed preliminary calculations, we can't yet find the perfect agreement between theory and experiment, but we do see a preliminary observation which states that if you look at the oscillation, again, with 100% contrast of the spin exchange cross-section between different isotopes of strontium plus, you see that the period of this cross-section occurs at actually exactly 2 times 2 atomic mass units, which is consistent with the fact that we see all even isotopes with the same cross-section and the odd isotope with a cross-section that is largely reduced. And this is the first indication of S-wave behavior far away from the S-wave regime. We actually went and performed another experiment, this time looking at charge exchange, where the chemistry ion wasn't strontium plus, but rather rubidium plus. Again, here, if charge exchange occurs and rubidium is being initialized at F = 2, this can lead to the release of hyperfine energy, which can be read out by the logic ion. And by performing this experiment, we were able to show that the rubidium plus rubidium charge exchange cross-section is about an order of magnitude suppressed than what we expect it to be from the semi-classical approximation. Again, indicating that S-wave behavior here plays a role far outside of the S-wave regime. So this is actually a good place to stop and ask if there are any further questions.
Hey, sorry, I had a quick emergency, but now we have indeed 2 more questions. Let's cut it short so that there is enough time for the rest of the talk. Regarding the micromotion induced heating, is like you mentioned Marco's paper, right? Is there can one think of this as a runaway scenario? Like you take one collision, it leads to a high emotional state, and then the fact that the ion is in a high emotional state makes it even more susceptible for further micromotion heating?
That's exactly the picture. And that's also the mechanism behind generating a power law distribution. If you look at a random variable, which is a sum of many small random variables that are uncorrelated, that would always lead to a normal distribution, to a Gaussian distribution. However, in this case, as you indicated, the different random variables are fully correlated. And that is because the energy you can gain in a subsequent collision depends on your energy. And that depends on the energy you received in the previous collision. So in many ways, this is like an all-in casino. You gamble on all your money, and if you win, you can again gamble on all your money, and if you win, you can again gamble on all your money. You don't need a streak of more than 10 or 15 such lucky consecutive wins before the amount of money you have is completely ridiculous. And this is exactly the mechanism, the engine behind creating these crazy energetic events that the power law distribution predicts. So that's a very good picture to have in mind.
Yes, other question. So in your introduction, right, you mentioned that these atom-ion interactions really are responsible for the molecule formation in interstellar space. Question is, do people see signatures of any of the phenomena you described, you observe in your lab, also in astrophysical observations?
So that's a good question. I don't think people have, in out-of-stellar observations, I think that the dynamics is limited to a few Kelvin and not down to the millikelvin, microkelvin range. We look at, and also I think that in out-of-stellar observations, people don't have the scrutiny and the control level that we have, that we clearly have in the lab. So I think there's still a gap between what can be done in astrophysics and what we can do in our experiments.
Right, yeah, in the interest of time, let's continue with the talk now.
Okay, so the last part that I wanted to quickly show is the observation of trap-assisted formation of atom ion molecules. So again, when we look at the free atom and a free ion colliding, I've described the Langevin image with inward spiraling collisions. The Hamiltonian in this case is the sum of the two kinetic energy terms and the polarization potential between the atom and the ion. But this is not really the situation in our experiments. In our experiments, the ion is strongly trapped, and we need to take into account the fact that there is a very strong pseudo-harmonic potential which localizes the ion. And in this case, this system is no longer translationally invariant. And because it's not translationally invariant, now the center of mass and relative motion are coupled. And if we look at the coupling term between center of mass and relative motion, again, this coupling term would be proportional to the reduced mass of our system. In the case of atom and ion, which have very similar masses, such as in our case, this coupling can take energy from relative motion and move it into the center of mass motion, leading to the formation of bound states in elastic collisions. So if we look at a trajectory that we can calculate in a simulation in which a rubidium atom and a strontium ion approach each other, they kind of get sticky at short range, collide over and over again, and then depart. Energy can also go back from relative motion into center of mass motion. If I draw their motion in the center of mass frame, I see these nice cloverleaf shapes. This dynamics was again predicted by Marco Settina in his paper from 2012, and is related to observations that happened using atomic collisions, ultracold collisions in non-harmonic potentials, and are related to confinement-induced resonances. If you like, confinement-induced resonances could be the quantum way with which these molecular formations are being described. So how would we be able to observe the formation of these bound states? Again, we're going to use electronic spin exchange as a tool. Now, how would I think of electronic spin exchange probability in the presence of these bound states? Now, the first thing I can say is that if I form a bound states and short-range collisions happen again and again and again and again, the probability for spin exchange would be enhanced. Now, I'll have a slightly different behavior if I look at spin exchange interactions that are exothermal or endothermal. If I look at spin exchange collisions that are endothermal, the Weizmann energy that is released in spin exchange can lead to the dissociation of the molecule. Now that, of course, depends on the magnetic field that I apply that determines the Weizmann energy of the atom and ion. Now, if I think of a scenario where I have many molecular collisions, and the magnetic energy the magnetic field is large enough such that a single spin exchange collisions would dissociate the molecule, I will find myself in a situation in which spin exchange probability would saturate to 1, because eventually I'm going to have a spin exchange collision that would break the molecule, and once the molecule is broken, the spin is stuck in the flipped state. However, if the magnetic field is very, very low, then spin exchange would indeed occur, but it can occur also in the other way around. So in the limit of having many molecular collisions, short-range collisions, and magnetic energy which is not sufficient to dissociate the molecule, the spin exchange probability would saturate at a value of 1/2. So the first thing we wanted to see is to see that indeed when we go to low energy collisions, spin exchange probability is being amplified. So the experiment we did was the following. We controlled the energy of the ion again by pushing the ion away from the RF null of the trap, forcing it through micromotion, and scanned the energy of the micromotion and measured the spin exchange probability. The red data here is the data that you see for exothermal reaction rates, and the blue data is for endothermal reaction rates. You see that for endothermal reaction rates, indeed, at low energies in which molecules can form, we see a sharp enhancement of the spin exchange probability. Whereas when we go to high energies, we see that the spin exchange probability is being reduced. In the endothermal reaction direction, the spin exchange probability is suppressed. That is because at low energies, we don't have the energy to pay for the spin exchange cross-section, and these two data sets at high enough energies agree with each other. Now, by looking at this data, we could fit it to a simulation and extract the spin exchange probability for a single collision. Now, this sharp enhancement is a very clear indication of the formation of a bound state. The next thing we did was to now measure the spin exchange probability as a function of the magnetic field. And what we see here indeed is that the spin exchange probability that starts at a relatively low value is being increased as a function of the magnetic field in the endothermal reaction direction, which is consistent with a change of saturation from closer to 1/2 to something which is closer to 1. In the endothermal direction, as we increase the magnetic field, the spin exchange probability, as we expect, is being reduced. And what you see here by the dashed curve here is the result of a simulation using the spin exchange probability per single collision that was taken from the previous set of data. And you can see that we get rather good agreement. So by taking these two experiments, we can actually use a statistical model with which we look at the number of collisions that we expect in the molecule and the probability of spin exchange, and from that look at the amplification factor at low versus high magnetic field, and from this amplification extract the average number of collisions that the atom ion experience when in the bound state. We see that we get about 8 collisions, and because we know what the polarization potential look like, we can actually calculate the period of a single oscillation, from that extract the lifetime of the molecule. So from our data, we could actually both determine the lifetime of the molecule of about 1/2 microsecond, as well as the depth of the molecular bond, which is given by the magnetic field that dissociates the molecule, of about 700 microkelvin. So that brings me to the summary of this talk. So I was able to show you results of 2 experiments coming out of our atom ion mixture experiment. One experiment in which we were able to see signatures for quantum interference effects in scattering far from the S-wave regime, and another experiments in which we were able to show the formation of atom ion molecules in elastic collisions due to the presence of the strong pole trap on the ion. So I'll end by showing the heroes that actually contributed and performed the experiments. This experiment is we started working on it quite a few years ago, 13 years ago or so. So there were several generations of graduate students and postdocs who worked on this experiment, and these are their names. And also thank the rest of the Weizmann Institute trapped ion groups and the agencies that that fund us. And I'd like to end by showing you this picture. Do you recognize this picture, Shimon? That's a picture of Nitzanim Beach, which is about 20 minutes drive away from the Weizmann Institute. And the reason I'm showing you this picture is because we have available PhD and postdoc positions. So if you'd like to come and do your research 20 minutes away from this nice beach, then let me know.
Right.
So,
thank you very much, Roee. I actually thought when you showed the picture from the beach, you're inviting atom ion pairs to take, a seat on each individual. We got maybe, already kind of late, so let's get two more questions. First one was the this first spin exchange plot you showed, right on the x-axis had positive and negative energy. On the other hand, it seemed you achieved this by exactly. So I think the question is you seem to achieve this by tuning the polarity of the compensation voltage offset. So does that mean you actually expect this plot to be symmetric around
let's see which plot. The first plot of spin exchange?
No, sorry. Actually the one where you plot the excitation probability in this molecule formation process.
Oh, I see. Gotcha.
Yeah, this one. Exactly.
Yeah. So right. So this is really the compensation voltage in units of millikelvin that we apply. And because we symmetrically move the ion away from the RF null into equal amplitude of micromotion, we do expect this figure to be symmetric.
It should be symmetric. Right.
Yeah.
And maybe last question. So with this strontium-88 ion, which is also known as a clock ion, if you would actually place this in a long-lived clock state, how would that affect the interactions? Could that be some interesting direction?
Yes, so thank you for that question. We actually have, we performed an experiment and published it in PRA, I believe 3 years ago or so, where we initialized the ion in the metastable d5 level and investigated what happens when the ion collides with the neutral atoms. And what we've seen is that this collision leads to excitation exchange. So collisions with about 30% probability lead to the ion departing from the d5 level and ending up either in the d3 level, emitting about 1,000 Kelvin of energy, or going from the d5 to the s1/2, but rubidium is being excited from s1/2 to the p1/2 or p3/2. So the electronic excitation is actually exchanged between strontium plus and rubidium, and we were able to detect the different paths by measuring the energy which was released, which was in the thousands of Kelvin. But as I said, since the ion is trapped in pole traps that are 10,000 Kelvin deep, we're okay. We're not losing the ion this way. An experiment we're actually doing these days exactly is to measure what happens if we start at a superposition, a clock superposition, a superposition of the s1/2 and the d5 in those occurrences in which excitation exchange did not occur. What happens to the phase between s1/2 and d5? And preliminary indications are that the phase is completely lost. So there's full dephasing in these collisions. This is somewhat different than what people observe, for example, in neutral atom clocks, where collisions lead to a shift and not to full dephasing. So shifts suggests, in my mind at least, is that a single collision leads to a very small frequency shift. And then when you have many collisions, the average is a phase shift and not phase dephasing. Whereas in our case, it seems like a single collision is enough to completely dephase the clock superposition. But as I said, this is still work in progress.
Great. Thank you, Roee. Let me close the seminar by mentioning the speaker in 2 weeks. It's going to be Sebastian Hofferbert, and yeah, from the University of Bonn. We'll hear about interesting QED effects with superatoms. Thank you very much.
Yeah, thanks, Roee, for a great talk. That was really great. And yeah, thanks again for doing it. Yeah. Chag Sameach.
Chag Sameach. Bye-bye.
Bye.
Bye.